morning, everyone. We are Team DPS, Dylan Prince Sean, and we've created a COVID skin surface temperature monitoring system for small businesses. My name is Sean McNamee, and I'm a computer science major.
My name is Prince Hossein. I am a senior bioengineering major.
And my name is Dylan Finn. I'm a junior computer science major.
For this presentation, we'll first look at the problem we're trying to solve and our motivation for doing so. Then we'll take a look at existing systems and dive into a detailed look at our proposed system, as well as how we implemented and tested it. We'll overview what each of us did, what we wish we could do, and then end with our references and Q&A.
Due to the COVID-19 pandemic, it is up to offices and businesses to ensure the health and safety of people as they reopen. It is their responsibility to follow occupancy guidelines and do health screenings. The traditional method of health screening requires a personnel to use a handheld temperature screener. The issue with this being that a personnel is required for operation, which compromises on personal safety. We aim to provide an automated and safer health screening solution. Our solution will be a self-service kiosk that screens customer temperature and reports abnormalities to key staff through an automated process. All businesses are now tasked with ensuring health and safety, or they risk being shut down and fined. After doing research for tools, we saw that there were automated temperature kiosks already developed. However, most of them were extremely expensive. Most automated kiosk prices were around the $3,000 range and also required an additional monthly subscription to be used. We believe this situation is unfair to small businesses. While big businesses may be easily able to follow the new guidelines, it may not be as easy for mom and pop stores. These small businesses may not have the resources or financial ability to purchase an automated system. Our motivation behind this project is for the small businesses. We want to provide an automated and affordable temperature screening solution for small businesses to help fight against the pandemic.
So since there was plenty of these pre-existing solutions out there, we had plenty of existing systems to pick and choose from in order to either gain inspiration or to pick aspects of which we wanted to ensure we were leaving out. Here we're going to be referencing 3 specific similar existing systems that we researched out of the 20 or so that we researched in total. First, we'll have the Lamasitech Zentron kiosk. Then we'll cover the diversified vital sign kiosks. And finally, we're going to talk about the RMS Omega kiosks.
First is the Lamasitech Zentron kiosk. Overall, it looks like a tablet with an extra sensor, but it can be mounted on a wall, put on a desk, or placed on a stand. On top of the temperature checking that all the systems we looked at have, this includes facial recognition, mask detection, and access control. Basically, these 3 make sure that any unverified users, any users without a mask, and any high-risk users are not allowed into a building. In any of those cases, staff are notified via email. For access control, it keeps a log of users and their entry times. Overall, the Zentron kiosk is a beast. It could read temperatures in about a second, and it has overall great features. The only bad side to this is its price point, about $2,700 to $3,500.
Next up, we're going to discuss the diversified vital sign system. Well, the diversified vital sign system doesn't have the range of features as the Lamasitech does. It does include something that we found very important. The diversified vital sign system is customizable and includes expandability into other systems via its own API. The level of customization that you can obtain with the diversified vital sign system is something we found to be very important when designing our own system. And as well, the diversified vital sign system has a lower price point of a $450 per month subscription plus installation fees. However, we still found that to be too expensive for our target demographic.
Lastly, the RMS Omega. The RMS Omega system begins with the pedestrian approaching the unit and having their identities and temperatures screened. The temperatures are scanned using facial recognition camera and a thermal detection camera sensor located on top of an Android-based tablet. The scans are quickly read and accurately saved to a secure back-end software system. The software allows monitoring in real time at each device location. In the device management, you're able to see a daily read and record of every customer. There are multiple station options based on where you want to position your uh, tablet in your facility. The RMS Omega SmartPass software provides data tracking for all employees and visitors. The cost of this whole system begins at $2,000 for the tablet alone and goes up to $2,600 for the full kiosk system with a stand. There's an additional $360 monthly subscription charge for the backend system.
Now that we've talked about some of the pre-existing systems, let's talk about our own proposed system. For our proposed system, we have three key aspects: our hardware, our API, and our user interface. For our hardware, we're going to include a thermal scanner, of which you can see an artistic rendering, which will connect to the business's LAN wirelessly in order to communicate with the host server also hosted on the business's LAN. The API will be the method of which the thermal scanner communicates with the host server on the same LAN. The API will be hard-coded into the back end of the server and will follow the RESTful design philosophy. Finally, our user interface will display the information sent to the server and registered in the database via the API. The user interface will be accessible either by directly connecting to the IP address of the host server, or by creating a custom DNS entry on the network.
Next up is our users. We've separated the users into hardware users and user interface users. Customers are the hardware users, and they have their temperature taken and will receive feedback from the system. The main user interface users are employees and business owners. We can also consider registered users here, but they aren't considered full users because they cannot view records from the website. Only registered users that are promoted by the business owner can view high-risk data and receive notifications. Here we see our context diagram, which is much like the users of our system. You can see that customers can have their temperature read and receive a response. Employees can log in and receive notifications via the website and emails and high-risk customer information. As well, business owners can update privileges of employees and receive login notifications. A closer view of our context diagram is our data flow diagram. Customers can still send their temperature and stand near the system. As they stand near, a proximity response will tell them if they have to get closer or move further away. Once they're at the proper distance, their temperature is taken. If it's acceptable, a cleared sequence will start and they will be cleared to enter the building. If abnormal, a warn sequence will begin. They'll be given feedback and their temperature, and the warn sequence will alert the API. The API will take the customer information and store it onto our database. As well, the API will notify our website. The website will then send an email, website notification, and a blinking navigation bar to the user, to the employee in the website. If they're logged in, they can view the data. To make sure they're logged in, the business owner can update their privileges. They update them, and that updates the Okta user accounts. As well, when a user logs in, the business owner will receive login notifications.
Finally, we come to our table schema. For storing our data, we settled upon using the MySQL DBMS system. We did this to provide further expandability for ourselves and for third-party developers. For our system as its base model, we utilize a single table that contains 4 fields. All right, an ID, an auto-generated ID, which acts as the primary key for the table, a timestamp, which is the exact time and date at which the image was taken, the location of the image, in which the file location of the image on the server which is stored, and the temperature of the person whose picture was taken.
Next up is our implementation. We'll look at the UI, API, and the hardware. First up is the UI, and specifically its pages. In terms of the pages, we utilize Node.js and Express for the organization, and a CSS file for the beautification. Here you'll see is the home page and the error page. The login page isn't included as one of the pages because it's just a redirect to our middleware, Okta, which we'll get into in a little bit. The high customers can be seen in this video. You'll see in the high-risk page, it accesses the most recent users, the most recent high-risk users of the hardware. Next up is the security for the website. We used Okta as a middle layer, and we utilized its accounts to create a project, groups, including the employee group, and a rule so that only employees can successfully log into the system. Therefore, while anyone can register for an account, only employees can actually access the system. Here we'll see that when a user logs in, they have to provide their credentials. After doing so, they are redirected back to the website and automatically to the high-risk user page. Last is our notifications. For notifications, we use the Notifications API and the Simple Mail Transfer Protocol. Here you'll see that when a notification begins, you can see the top blinking bar, as well as a notification appearing from the Notification API. If a user does not see the notification, they will see a email right here, where it gives them information about the user. So if they don't see the navigation bar blinking, they will hopefully see the email that appears. You'll see this is a closer look of that email that they received.
Finally, we come to the API. As I previously mentioned, our API is hard-coded into the back end of our server and is the method of communication for our thermal scanner and any third-party devices which to access the data in our databases. We use the REST API model, which stands for Representational State Transfer. A REST API allows you to communicate with the database via specified HTTP post and GET requests. In our case, we use primarily post requests because it allows us to include a JSON body in which we can include JSON text variables and images in order to autofill custom SQL queries to retrieve and update the data that we wish to access. To test our API and to implement it, we use a software called Postman, which allowed us to easily send HTTP requests, primarily post requests in this case, and see the response data without having to deal with the browser's inspect element feature.
And for the UI and API implementation, we used Visual Studio Code as our editor, and Git as our version control, and GitHub as a repository storage.
Our whole circuit was implemented using open source components like Arduino and Raspberry Pi to keep costs low. Let's briefly go through each component, beginning with HCSR04. This is an economical ultrasonic distance sensor. Next, we have the MLX 90614 ESF. This is an infrared thermometer designed for non-contact temperature sensing. It can sense as low as Antarctica, -70 degrees Celsius, and as hot as the boiling point of Mercury, 382 degrees Celsius. Next, we have Node MCU ESP8266. The ESP8266 is a breakout and development board with Wi-Fi capabilities. Close by, we have the OLED display, which can display a maximum of 16 lines of text content. And then we have the OV5642 camera. This is a 2 megapixel camera optimized to run on Arduino. Lastly, we have the breadboard, which was used for solderless prototyping. Next, we have some hardware changes. On the left, we have a Raspberry Pi 4, which is another breadboard, another development kit. On the right, we have the Pi Camera V2. This is an 8 megapixel camera module capable of 1080p pictures. These two components were added in later during our testing phases. I will explain why in a moment.
So next is our testing. Testing is imperative for any system that aims to meet its goals, and our unit testing was used for the UI, API, and hardware, while our functional testing will be shown with our demo. For UI unit testing, we have authorized users only. This shows that only people that are logged in can access the high-risk customer page. So see, we're trying to access that page, but it's only accessible when we're logged in. So you see, if I still go back to that same page, we can get there, but if I'm logged out, we can't. Next is our authenticated users only. You'll see that when a user tries to log in this case, smcnamee@myit.edu, they're unable to sign in. But if the business owner logs in and goes to their panel, they can go to the groups and add that user to the employees. So you'll see here that smcnamee@myit user was added to the employees group, and now after they're added and saved, that user can successfully log in. Lastly is records update. So in the high-risk user customer page, we can see the most recent customer, but if we add a new customer to it with a SQL statement, you can see the new customer appear.
Finally, we're going to come to API unit testing. Testing of all of our API functions were done via Postman, and primarily this testing consisted of sending new data and retrieving pre-existing data. However, a lot of what we did was tweaking the method in which the variables were structured, and there was a lot of trying to see if we could alter the way in which the SQL statements would process the data. The reason for doing this is in order to mitigate the pardon me. The reason for doing this is in order to mitigate the potential of an SQL injection attack, which is a real threat against us. However, through all the testing we did, we are relatively sure that our system is safe from modern methods of SQL injection.
Each piece of hardware was individually tested to assure that they were working properly and outputting the correct results. These tests were done through code testing and physical testing. Let's just begin with the HCSR04, the ultrasonic distance sensor. This sensor was tested by holding numerous objects at different ranges and making sure that it was providing the correct reading. The only time the sensor provided boundary readings was when it was pointed at something extremely smooth, like a pane of glass. This was because the sensor uses ultrasonic and these kind of surfaces refract the signal. For our application, we determined that this would not be an issue. Next, we have the MLX90614 ESF, the infrared thermometer. This was also tested similarly, holding objects of different temperatures. One of them being a hot pack and a cold pack. We held the hot pack and cold pack up near the sensor and then compared that reading using a handheld laser to determine if it was showing the proper reading. For our application, we determined that this was indeed providing the proper reading, and it is good for our project. Next, we have the OLED LCD. This was simply tested through code. We sent a bunch of sentences to this display to see if it was properly providing the display that we sent. Next is our hardware changes that I wanted to discuss, being the OV5642 camera to the Raspberry Pi Camera V2. During our early prototyping stages, we wanted to use the camera on the left because it was natively supported by Arduino. But during testing, we saw that the manufacturer did not provide proper documentation. So we had to abandon this component after 24 hours of troubleshooting for the camera on the right, the Raspberry Pi Camera V2. The Pi Camera V2 used a completely different language and architecture, which required us to change our whole code, but it was a necessary trade-off. Next change was the development boards. On the left is Node MCU, which was changed later to Raspberry Pi 4 during testing. Initially, we picked the Node MCU because it has a significantly smaller size and was capable of powering the whole circuit. But since we ran into the issue of the camera as discussed earlier, we had to switch to Raspberry Pi in order to support the new camera. This was a necessary trade-off to have our whole circuit functioning.
Finally, originally for our server, we were hosting it on the HTTP protocol. However, during recent testing, we found that a recent Google Chrome update would no longer allow us to push notifications unless they originated from a secure site when using the HTTPS protocol. So unfortunately, at the last minute, we were forced to learn how to implement SSL certificates. That way, Chrome would allow us to continue our notifications feature. This included, but wasn't limited to having to register a domain in order to get a service to provide us SSL certifications and deal with the troubleshooting, in which case followed that.
Next is our contributions of who did what. For myself, my largest focus was the user interface. For this, it included Node.js and Express pages, the organization of how you go from one page to the next, the manipulation of the W3 Schools CSS file so that we could have that blinking navigation bar so that pictures appeared in the proper spot and looked the proper way. Next is the security and authentication through Okta, making sure that when users logged in, they would be able to be redirected properly. Notifications in terms of the email and blinking nav bar, and overall organization using our burn down chart for our project.
Finally, we come to my contributions. I, along with Sean, helped create the backend of the server, and during that creation, I hard-coded in the API design. With that, I utilized Node.js and Express routes in order to turn HTTP post request handlers into a RESTful API. I also handled the middleware that involved the JSON text parsing and the middleware that established the connection and security to our MySQL database. Furthermore, I handled the installation and the design of our database, and finally handled miscellaneous networking issues such as port forwarding, SSL certificates, and networking protocols in general.
My contribution to the project began with hardware. I did research on the different components, as well as doing component testing for each individual piece, and creating different prototypes to see which one was better. Then I did circuit implementation, which was creating the different circuits, and finally connecting to websites. I connected the whole circuit to post images to the website.
As with any project, we have future work that we'd like to work on. In terms of the UI, we'd want to create data-driven graphs based on the customer information to give employees insights.
In terms of the API, we would like to be able to make the API routes more comprehensive. That way, whoever's utilizing our API has an easier, more logical route of getting to where they need to be. Furthermore, we would want to include better authentication to ensure that only people authorized on our user system are able to utilize their API.
To improve hardware durability, we would
Here are references, and I guess there's no Q&A because this is recorded. But I hope everyone has a wonderful day.
Hello everyone, welcome to the COVID-19 temperature monitor demo. For this demo, we will use two mugs, the one on the right with cold water having no fever, and the one on the left with hot water having a fever. Before we begin, let's quickly review the circuit. This is the overall circuit from top view. First thing we have here is the ultrasonic distance sensor. On top of it, the thermometer. Here's the USB running the operating system, and on top the Raspberry Pi camera. Let's move on to the LCD display. And this is the Raspberry Pi 4 powering the whole project. Let's begin our demo. We can see that the screen begins with "come closer" because there's nothing in front of the sensor. Let's move the mug with "no fever" in front of the sensor. Once it's at the correct distance, we see that the screen displays 64 degrees temperature. Go ahead. Now let's put this aside. Next mug is the hot water, the one with fever. Let's move this. In front of the sensor, we see it is reporting 125. Stop. Now I'll be handing it over to Sean, who will be showing you the website portion of this project.
Hello everyone, my name is Sean and this is the UI portion of our project. You'll see here we've received that last test sent from Prince, and on a typical day employees will log in. So I'll bring up the incognito window so you can just see that login because it automatically logs me in. So I'm going to grab that IP over here, and yeah, so the login will automatically redirect me to Okta, where I'll provide my login credentials. So I'm going to pop back to the auto read log and the high risk page, and we'll see what a customer do on a typical basis. So they could either be waiting at high risk or home, doesn't really matter. We're basically just waiting for a blinking red bar up top or an email to show us that a new customer is sent here. And the email, it knows which one to send it to by, well, you're logged in and you've provided that email. So that's how it knows what email to send it to. So we're going to wait for test 2. So Prince, you can send that over. And yeah, another thing to notice is that, yep, and here it is that only logged in customers receive these notifications. So that's a big thing. So we're going to check out the email.
And oh, yep, here it is. We got a new email. And if we click on down, and you see we've been tested a bunch, but we see it's 10:59 right now, and we have 10:58:47 and a temperature of 120 degrees. So we'll see for that 10:58:47 when we go to the high risk customer page. Yep, 10:58:47 and 120 degrees. Yep. And if we scroll down, we can see all of the customers from the last 24 hours. So you can see we did a lot of testing, but up top we see those last 2 that Prince sent. Thank you very much.
My name is Dylan Finn, and for my aspect of the CSCI 318 term project, I created the database system. I handled the connection of the database to our Node.js server, and I created the API system, which is hard coded into the back end of our Node Express.js server. Now, starting with my demonstration of our database management system, we chose to go with MySQL, and rather than doing just storing our variables in a JSON or a CSV file, we chose to go with a relational database system and a table. That way we provide for future expandability, or we make it easy to integrate in our customers' pre-existing tables. Furthermore, Node's NPM, or Node Package Manager, provides an easy-to-use connection package for MySQL. Now, as you can see, I've already logged into our database. I'm going to select the proper database, and I'm going to display our current tables. As you can see, we only have one table entitled Records. This is on purpose because we only need one table to operate our system. Inside of that table, we use, oops, my bad. We have 4 columns total. We have respectively our ID column, our timestamp column, our image location column, and our temperature column. Our ID column is an auto-incremented integer which acts as a primary key, in order to make retrieval of the data easy, and to easily integrate into or expand into a full relational database. Furthermore, the timestamp is generated by the API through the SQL Server upon submission. Our image location and our temperature, which are respectively a varchar or a string, and a double, are two fields which are provided by the thermal scanner to the API, inserted into the SQL string, and then sent to our database. Now, to handle this connection, right here we have a file entitled connection.js. The purpose of this file is to create the connection to the database, which you can see right here. And the way this is handled is by creating using the MySQL package, running the MySQL.createConnection function, using in there, storing our credentials, and then storing that as a connection, as a variable entitled connection. We can initialize this connection by doing connection.connection, and either throwing the error and entering into the console that the connection failed, or just simply displaying that the connection succeeded. To export this variable to the rest of our system, we use the line module.exports equals connection, and from here you can see this is referenced up here and is renamed to DB, which is short for database, to be referenced further in our system. Down here, real quick, you can see the code we use for processing images. The package we use to process images is referred to as Multer. Multer handles incoming image files through HTTP post requests, de-encodes them, and stores them in the location in which you wish them to be stored. Now, for our API, we have two primary important functions that are used. The other two included in here currently are for testing purposes. Right here we have our router.post, which points to API/red alert. This is the function that will be used by the thermal scanner in order to send an image, a file name, and a temperature if somebody with abnormal temperatures is detected. To do this, we use the upload.single, and then we have used the upload.single function included in Multer, and we pull from that file the original file name in order to store in our database. We store this variable as file name. Furthermore, we then parse the JSON body portion of the post request. Assuming that the proper variables are used by our thermal scanner, then we will be able to pull the temperature variable and store that in a secondary variable known as var temperature. From here, the way our SQL queries work is we store an SQL query as a JavaScript backtick string. We use the backtick strings. That way we are able to reference other JavaScript variables such as file name, which we stored up here, and temperature, which we have right here. This SQL statement inserts into the records table, omitting the ID column because that is auto-incremented on its own. We call the now function, custom integrated into MySQL to get the current date time, and then send through our file name and our temperature that we parsed from the thermal scanner itself. Next, we have our router.get display high risk. This is one of the very few GET requests that we handle in the API. This GET request will only do one thing, and that is sending the SQL statement select all from records where the current timestamp, where the field timestamp is greater than the current date time minus a 24-hour interval. In layman's terms, this simply will display every record in every row in the records table between now and the last 24 hours. Then we order by the ID in descending order. That way the most current insertion will be displayed first, and then the rest will follow in order of insertion. This has been the API portion, and I hope you enjoyed the demo of my work.